Good afternoon. Good afternoon, everybody. Good afternoon and welcome. Welcome to the Physics Colloquia series. This series of talks brings together world-leading experts to discuss advancements in their fields. And today we have Andrea Cavagna. And so do you want to introduce Andrea?
Sure. Yeah. Okay, so it's a real pleasure today to introduce Andrea Cavagna. I've been knowing Andrea for quite a long time now. He's a good friend of mine, of course. And well, actually, since I met him when he was a bachelor student and he managed to snake into my apartment in Trieste. I was at the seaside at that time and managed to remain there for almost 1 year. It was a great year. After that, he got the bachelor degree in Milan. And then he moved to Rome, working with Giorgio Parisi group, and got the PhD there. Then he moved to the UK, first to Oxford, and then to Manchester, and then came back to Rome, to Italy, at the Institute of Complex Systems. When he gradually shifted his scientific interest from originally spin glasses to living system, as you will see today. So it was actually a good idea, apparently, because he then got an advanced ERC grant for this kind of research in 2018, and got an award, an important one, an IPS award for biophysics, the Hans Delbrück Award, in 2021. So again, I'm very, very happy to have Andrea here today. And Andrea, stage is yours.
Thank you. Thank you. Thank you very much. And so, thank you for inviting me here. It's a real pleasure to open the Colloquium season. And so you see that you have your laptop open. So you know, in the old days, you could walk out from a talk anytime, but there was a price you have to pay, you know, to stand up, and everybody was looking at you. Now you can just switch your side from the talk to the laptop, which I think is great. Anyway, so I would like to start with a quote. Okay, it's not working, sorry. Okay, yeah, it's a quote by Kenneth Wilson. It's kind of the hero of this talk. He was more or less, no, not single-handedly, but one of the fathers of the renormalization group, which will be the topic of this talk mainly. So he says, one of the more conspicuous properties of nature is the great diversity of size or length scales in the structure of the world. And this is, of course, not only true for physics, it's not only a problem in physics, but it's very much the case also in what I do, which is collective behavior in biological systems. So you do have collective behavior from the very short scales. This is a colony of stem cells growing, well, accelerated growth of a colony of stem cells. You do have collective behavior in insect swarms. And today I will give you results in the second part of the talk. I will give you results on this kind of system, so swarms of insects. But you have collective behavior also in vertebrates, in fish, mammals, and of course you have collective behavior in bird flocks. So the problem of the many scale of lengths is twofold. Well, first of all, collective behavior spans many scales in space and time in biology. But the most important problem about length scale is the fact that even in one single system, you do have many scales, from the microscopic one to the microscopic one, that may be interacting with each other. So they're not decoupled. So if you go to Fourier, they are not decoupled. So this is when the system is really hard, when you have the emergence of collective phenomena, but all the scales are coupled to each other. So how do we tame this complexity? And in particular, how do we tame this complexity in biology, where you have this problem of the scales, and then you have the problem that every single organism seems so different from all other organisms. So if you're a physicist, you do that by doing really outrageously minimal models. So very, very simple models. Well, at the end of the talk, probably they will not seem so simple to you, but let's say you're not supposed to understand this equation now, but the idea is that to condense in a set of differential equation the behavior of many different living organisms at the same time. And this is something that really pisses off biologists a lot. So the idea that you can simplify biological systems so diverse and complex and tremendously rich in details by these very, very simple mathematical and physical models. So, and they have a point. So what is our justification to do that? Well, the justification that we have as physicists is this sentence that more or less we always write, at least we statistical physicists, in all our proposal and papers and so on, which is macroscopic details do not matter much when large-scale structure emerge in the system. Which, of course, would be very nice if it were true. The point is, okay, but who says so? So how do you know that this is true? Okay, because effectively, different biological systems, like different physical systems, they are different at the microscopic level. So they do have different Hamiltonians, they do have different dynamical details running their behavior. So how do you know that this is true? Well, the tool that we have as physicists, that is more or less always ingrained in our soul, that is telling us that this is true, is the renormalization group. Okay? So the renormalization group was this great idea that was developed by all these people who, in the last century, they were struck by the fact that you could have very different physical systems, from ferromagnets to fluids to alloys and so on, having described by the same physical laws, in particular the same diverging power laws. So we would say the same set of critical exponents. And that seemed like a miracle at the time. How was that possible, that these two very different systems, like the ferromagnetic transition or the liquid vapor transition, could be described by the same laws? So this was called universality. And it was very surprising because it seemed that the more complex was the system and the more universality worked, okay? And so there was this big effort, which at the beginning was a phenomenological effort with the introduction of scaling laws and so on, that culminated with the work of Wilson, and in particular with this work by Wilson and Fisher called critical exponent in 3.9 dimension, which was the formal layout of the idea of the renormalization group. So what I will try to do, and this is the colloquium part of the colloquium today, is to give you a very pedestrian idea of what the RG is. So first of all, I hope that there are at least some students here who are not fluent in the renormalization group. Otherwise, I will just embarrass myself. Also, if you are a particle physicist, this will not look to you at all like what you mean by the RG. So there is no Callan semantic here in any way, okay? But so it's a very qualitative way to explain the renormalization group. So the basic, very intuitive idea of the RG is, yes, these two systems are very different from each other at the microscopic levels. They have very different details. But if you look at them from far apart, from a large enough distance, they look the same. So this is a very intuitive idea, but also very problematic because there are 1,000 problems with this statement. First of all, what does it mean to look at the system from a certain distance? How enough is far enough? And what does it mean to say they look the same at the quantitative level? Okay, so this is what I will try to explain you today, mostly using Google Maps, so it will not be very quantitative, but to convey the idea that RG is actually a very great conceptual tool. Okay, so systems do differ at the microscopic level. So let's take as an example, sorry, I have a desync between, okay. So, I hope this works because this is the core of my talk. Anyway, so we have two cities, Bangkok and London, and we concentrate on two temples, two different temples, so whose name is that one. And they have very, very different microscopic details. And what is important here is to understand that the dynamics, the probability distribution and the dynamics producing the probability distribution that produce these two configurations are very different, okay? It's not only that this one configuration to be different. Now, the idea of the RG is just now to zoom out exactly as you would do in Google Maps. Now, I hope this works, otherwise I'm screwed. Let's see, yes. So this is what happens when you're just zooming out with Google Maps. So this is the basic idea of RG. If the stunt worked, you should see that the two cities, the two systems at this scale, they differ from each other much less than they did at this scale here. So on the short scale, you see I have all this huge variety and difference in the details, but at the large scale, you do get very similar systems if you look from far apart. However, you may say, okay, this is still very qualitative, but the problem is you have done nothing. You're just looking at the system at a different scale, but the details are still there. The fact that you're looking at a different scale doesn't mean that the details are not there. So Westminster Abbey is still there, you may say. And so you're just doing something with the resolution of the display, so I don't see it anymore, but it's still all the microscopic details, the microscopic information is still there. Well, is it? So if we zoom back, this is what happens. So this is what the RG does. So it's not a reversible transformation. So you have actually erased information when you do the RG transformation. So the idea is that the RG transformation is made up of two steps. And the most important one, the one which is more loaded with information and with result, and which is the one connected to the appearance of Feynman diagrams and so on, is not the zooming part. The most important part is what is called the coarse graining. Coarse graining, which really means a local erasure of information. You're locally averaging the system in order to make some coarse graining, and so in so doing, you are irreversibly erasing information. Once you do that, you do the second step, which is the following. Once you have erased information, you have also changed the size of the pixel. So here the pixel is the smallest, is your smallest resolution, okay? When you average locally this image here to produce this image here, you produce larger pixels. So what you do then is that you do a rescaling to restore the size of the pixel, which in momentum space means that you first change the cutoff in k-space by a factor b, and then you rescale everything in order to restore the same cutoff. Physically, you do that because then you will want to compare different theories with the same cutoff. Okay, so you end up with a system, and imagine that the system is in the bulk. You're not changing the total size of the system because that is infinite. And so you end up with a system which really looks the same, but is not the same. So smaller features are blurred, okay, but the largest one are unaffected. And so the new system has the same large-scale behavior as the old system. But the question then is, okay, what is good about erasing information at the short scales? Why did you do that? So there are two answers here. One which is not very illuminating, which is, okay, because now you have less degrees of freedom, so the system is simpler. But this is not actually fundamental at any level, because especially if the system is infinite by itself, you're just divided by b, an infinite number of degrees of freedom, so you're not gaining much on that side. So the reason why this is important is that because in doing this transformation, so in blurring the system and looking from far apart, what you're doing is that you're changing the interactions of the system. So in other words, when you do this, okay, you have a new system described by new probability distribution. Now, we know that this will be some Hamiltonian or some dynamical equation, so the Hamiltonian, the system is defined by a set of couplings, okay? So all those parameters which define the probability distribution of that system. So when you do this transformation, what you're doing is that you may be changing the coupling describing the system. And what is interesting is that in the easy case, which is basically only the Gaussian model, but in the case in which all the length scales do not interact with each other, when you have the coupling of the K modes, of the Fourier modes, then in that case, the interaction of the system do not change by doing this coarse graining and zooming. But in all the interesting cases, the non-linear cases, the non-Gaussian cases, in which you do have something interesting going on in the system, in which all the different length scales are coupled to each other, then you do have a change, so a motion of the coupling constant. So this is the crucial point. You're doing this to see how the coupling flow in the space of parameters by doing this renormalization, by doing this coarse graining. So you're asking, okay, if I erase the microscopic information and I look at the system from a larger distance, how do I change the couplings that produce the probability distribution of the new system? And why this is very important? Because in some cases, what could happen is that this flow, which is a flow which brings one system across the space of parameters, another system across the space of parameters, and so on, in some cases, you can have that all these flows converge to just one fixed point of the flow. So when this happens, what it means is that you have that Rome flows to the same fixed point, Paris flows to the same fixed points, London, Bangkok, and so on. And so this means that that fixed point reproduces, describes the long-range behavior of all those systems, irrespective of their microscopic details. And that was the way in which the renormalization group explained universality. So the idea was that when you really not only look from further apart, but you really integrate out the microscopic details, you move in the phase space, and systems that look so different from each other at the microscopic level become the same system at the large-scale level, okay? And this, of course, was huge, because that was the final proof of why you could have that the liquid-vapor transition was described by the same physical laws as the ferromagnetic transition. Because the starting point was very different, like London and Paris, or London and Bangkok, but the fixed points of the lambda phi 4 theory was the same for the two systems. So this is how the RG produces this flow, which is the famous flow of the renormalization group. And this is the fundamental reason why physicists like to play with toy models. The idea they have is, okay, I'm hoping, even though I'm not writing that, but I'm hoping that the system I'm studying actually belongs to the same fixed point as my very simple theory, which of course is something that you should prove, but even when you do not prove it, this is the idea you have in the back of your mind, okay? Now, the big problem is, does it work also in biology? So biology has an enormous complexity compared to physics. We are not asking whether does it work in the development of a single cell, of course, because you are changing scale, so you need a collective system. So you need many degrees of freedom, right? So you need groups. So this is why you ask whether the RG works, but in the context of collective behavior in biological system. But still, even in collective behavior, so in swarms, which is what I will show you today, it's a long shot in saying that because it works in physics, it must work also in biology. So this is what we try and check. Any question up to now? I'm afraid this is the end of the funny part, so if you're so amused at the end of this part, I can only imagine at the end of the second part. Anyway, any question? Students? All clear? Okay. So the RG was the pinnacle of a long chain of things. So first of all, people understood that there were stronger correlated systems, and that those correlations, which looked very messy, were governed by scaling laws, okay? I will not go through that, but let's say that in the last 10, 15 years, there is evidence that also in collective biological systems, you do have strong correlations, and that you also have evidence of scaling laws, a little bit like in physical systems. So you can simplify the big diversity of the correlation function by having, by formulating some scaling laws. So these are the two stepping stones, or if you want, the two necessary conditions to start talking about the renormalization group, which is what I will try to do today. I will try to do that. We have done that on real swarms of insects. So what we did was first experiments. So let's measure some critical exponent, and then theory, and try to reproduce that critical exponent, okay, the whole thing. So I will not give you any details of the experiment. I would just like to to put in your mind that, yes, we do experiments. So my final theoretical result will not be just compared to simulations, but to actual experiment in the field. These are the bugs. We consider a couple of species, 5 different species, and these are the things that you see in the parks all over any city in the world, okay? So really swarms of non-biting midges, so they're not nasty guys. Okay. Once you have the images, you have to do the tracking, which is really a lot of work. I will not give you details on that, but just to tell you that the computer vision part of this project was huge, because you have all kinds of occlusions, you have many cameras, sometimes the bugs, so these are birds, but we use the same technique for birds and insects, okay? So you have to solve the computer vision part first, and after many years that you succeed in doing that, you do have the 3-dimensional trajectory of each individual in the swarm, or something like that. Of swarm, in our case, of up to 1,000 animals. So it's not the Avogadro number, okay? So it's still pretty good. Okay, so what do we measure and observe once we have that? Of course, we are physicists, so correlation function. So the first thing you could do is to study equal time correlations. Correlation of what? Well, you could do many things, but we focus on correlations of the velocities. So velocity correlation function at equal time, and if you the connected correlation function is very important. So you have to subtract, well, in the case of midges, of swarms, is not very important because there is no net motion of the swarm, but in the case of flock, where they all go in the same direction, if you do not subtract the mean, you get a very strong correlation always. So you compute the connected correlation function as a function of the distance, and what you find is that you have a structure. I will go back later to this structure, but the important point is the system is correlated, so it's not just a bunch of random walkers, which was actually the suggestion we had at the beginning, that they were just doing some random motion over some landmark. Well, they're not doing that because they have correlation. And if you define a correlation length, which you can do, what you find is that the correlation length seems to be growing with the size of the system. So the system is, even though with a lot of noise, in a sort of scaling regime at the static level. So you have a correlation length which scales with the size of the system. And then you can do temporal correlation, so to extend your velocity correlation to different positions and different times. And this is where you really would like to have scaling laws, and fortunately, this correlation function obeys all kind of scaling, so you can simplify them. The important point being that you can measure a relaxation time and the correlation length. Relaxation time, which is a collective relaxation time of the entire group, so let's say the smallest k in the system, and of the correlation length. And what you find is that you have some evidence of what in statistical physics we call critical slowing down. It is the fact that the relaxation time grows with the correlation length in the system. And this is a very deep thing in stat phys. And the idea is that if you have large correlated region, and if you want to relax the system, you will take a longer time, because you cannot just flip each single degrees of freedom independently because of the correlation. And the way space and time scales with respect to each other when you have critical slowing down is ruled by one exponent, which is called the dynamical critical exponent Z, which is one of the critical exponents, and is one of those small number which really nail down the universality class of a system, Okay, so it's one of those things that you want to calculate when you have a statistical physics system. So if we plot our log tau versus log psi, again, each one of these points is the real swarms of insect, okay? We get this exponent, z 1.37. So to put things in perspective, the typical value of z in the, let's say, easiest kind of system, like the Ising model, Landau-Ginzburg, and so on, is 2, or very close to 2. And so this is a small value of the dynamical critical exponent, and was not around in the zoology of the many statistical physics or field theory models before we did that. So what we want to do is to understand what are the physical, well, the theory mechanism leading to this critical exponent by using RG. So the 3 key experimental facts, so being very brief on experiment, is that we have a scaling system, which is important because we would like to be ideally at the critical point, but there is no notion of criticality, well-defined criticality here, because the system is finite. We don't know how to define criticality in any sensible way, but the important point is that we are in a regime where the correlation length is as large as the system size, okay? The second point is that we have critical slowing down, and the third observation is that we have this value that we want to reproduce with theory, using as few physical ingredients as possible. Okay, so let's do some theory. So the first ingredient that I will use is imitation, which is ferromagnetism. So it is well known in all this kind of biological system, especially when we are talking about the dynamics of the velocities that do not want to crash into each other. So when their distance becomes very small, typically these animals tend to align their velocities, more or less like in a ferromagnets, spins tend to align to each other. Okay, so this is why so many statistical physicists have been recruited by biophysics. Because biology is, at a very fundamental level, a game of imitation, and imitation is ferromagnetism. Okay, so this is why the Ising model was so easily exported into biology. Okay, so let's limit ourselves to imitation. Okay, so in this case, what we get is the vectorial generalization of the Ising model, or the classical Heisenberg model, if you want, in which you have the dynamics. So the sigma now are just unit vectors, representing the velocities of the animals. But again, these are not animals. There is no feature here. So an insect is very different from a unit vector. Okay, so remember that we were doing really toy models to describe a very complicated system. But the idea of this equation is just that you change your direction of motion by making an average of the direction of motion of your neighbors. So Nij is the connectivity matrix. Is telling you who is neighbors of whom. And so this first piece is saying that you are averaging the velocity of your neighbors plus some noise. Why? Because there is always noise, including in biology. I mean, there must be noise. And if you do the coarse graining of this microscopic model, so you work out a field theory, what you get is time-dependent Landau-Ginzburg theory, which is also known as Model A in the classification of Halpern and Heumer, which is the most basic dynamical field theory that you can think of. Okay? So where H is the Landau-Ginzburg Hamiltonian, which is also known as lambda phi 4. It has a grad square, a mass part, a nonlinearity. Okay, it's not essential that you get this if you haven't done field theory, but the important point is that you have that the only physical important ingredient here is mutual alignment, mutual imitation. This was the model over which the renormalization group was developed, both at the static and the dynamic level. So the critical exponent of this model has been worked out in '72 at the very beginning. The flow is a very simple flow because there is just one. If you are at a critical point where the mass is 0, you have just one coupling constant, which is u. And the critical exponent of this model, as I told you before, is about 2. Well, where is this 2 from? You can see it from here. You have a first derivative in time here on the left, and the second derivative in space here because of the Laplacian of the grad square. So dimensionally is t and k square on the right. So the exponent is dimensionally very close to 2. Well, it's dimensionally 2, and the actual critical exponent is very close to 2. So this is very far from what we get. And when you're talking critical exponents, small differences matter a lot. It's not you say, okay, 2, 1.3, more or less close to each other. No, this is, I mean, the RG, people of the RG, Wilson got the Nobel Prize for a correction of order epsilon square, which was 10 to the minus 2. So, I mean, small correction in the critical exponent matter a lot. So clearly we're doing something wrong. And obviously we are missing a lot of ingredients. But before trying to put the second ingredient, let's try and understand what are we missing at the physical level. So the critical slowing down, which is telling you the time scales like space to the z, if you invert that purely dimensional analysis, so only a hunch, this is telling you that space scales like time to the 1 over z. Space or distance. Distance meaning the distance covered by the fluctuations. So that equation is telling you that a small critical exponent z means a larger exponent 1 over z, which means that fluctuation travel in a more efficient way. So a small critical exponent is telling you that in the system there is something which propagates fluctuation in a more effective way than in the, just in the Ising model. So there is one ingredient, an obvious ingredient in the system which propagates fluctuation more effectively than in the normal ferromagnet, and that ingredient is activity. That is, that these small arrows are not sitting on a fixed lattice, but they're actually going around. And of course, if you're going around, you're transporting your own fluctuation in a much more efficient way than just by interacting with the other people, okay? And that was soon recognized by Toner and Tu, that in active system, for example, in active system, you can violate the Mermin-Wagner theorem, which is not a violation because there is no theorem, but you can go against the Mermin-Wagner theorem, you can have spontaneous magnetization even in 2 dimensions, because you can go around and say to other people in what direction you're going, instead of just transferring the information from one person to another. Okay, so you add activity. Adding activity is, at the microscopic level, is simple because you have the same equation of imitation at the beginning. So you just do what your neighbor, the average of your neighbors do. But then, instead of just sitting on your network, on your fixed lattice, you follow your arrow. So you have now an Ri dot different from 0. So you align to your neighbors, but then what you're aligning is actually a velocity. And so you're moving. And because you're moving, the interaction matrix changes. And so there is a feedback between these two equations, and the system becomes much more complicated to solve. Okay, because the interaction matrix Nij now depends on time. And something nasty here is that you know that this could be written in the static case as a derivative of an Hamiltonian, but now if the interaction matrix depends on time, that is no longer an actual Hamiltonian. So you are completely out of equilibrium in this case. So if you want to do field theory of this, you have to do coarse graining, and this was what Toner and Tu did in the 90s. And the idea is that they had a flying ferromagnet, a moving ferromagnet, or if you want, a flowing ferromagnet. And so their idea was, okay, if this at the microscopic level is a moving ferromagnet, at the field theory level must be some mixture between a time-dependent Landau-Ginzburg, which is a ferromagnetic part, and Navier-Stokes, which is fluid dynamics. And so they formulated a theory which is really a join of the two things. You have the right-hand side here where you have the good old Landau-Ginzburg Hamiltonian, the derivative of that. But now instead of having a normal time derivative, you have a material derivative because you have a flow, really a flow of this active mass of birds. And you have a pressure on the right. To cut a long story short, they studied that in the incompressible case because, sorry, you have another field now, which is the density. At equilibrium, you don't have the density because everything is fixed, but now you can have density changes. But the simplest thing you can do is to study the incompressible case where the density is fixed. And they did that, and indeed they find a change in the critical exponent. So if you do RG, you find a new fixed point. So the equilibrium one, the one we saw at the beginning, the one with only ferromagnetism is Z equal to 2. But this is unstable when you add activity and you flow to another fixed point where the critical exponent is 1.73. So how good is that? It goes in the right direction. So clearly activity was a good ingredient, but it's not good enough. There is still something that we are missing. So we need a third ingredient. So to get what the third, that was our own original contribution. So to get what is the third ingredient, let's go back to experiments. And remember, a smaller z, which is what we need, suggests that there is a more efficient way to propagate information in the system. So we have already added alignment and activity. So there must be a third ingredient which is granting a more efficient transport of the information in the system. So what is that? So let's go back to the temporal correlation functions. Here on the left you have the one of real swarms of midges, the experimental one. And on the right you have simulation of the theory I've given you up to now. So a theory with alignment and activity. So clearly they are very different from each other. And as soon as you study the damped harmonic oscillator, you understand that the main difference is that the one on the left is underdamped, or looks underdamped, and the one on the right looks overdamped. So it seems that the theory we're doing is overdamped, while reality is underdamped. And indeed, if you solve just the stochastic harmonic oscillator with the inertia, friction, and harmonic potential, depending on the ratio between friction and inertia, you can go from the underdamped regime, critically damped, and then the overdamped regime. So it seems that we are doing a theory like that, while the actual system is like that. Well, okay, you may say, why this should help? So you're giving me another reason why the current theory is not working. Okay, but normally when you have two ways in which something is not working, sometimes they cooperate to give you a hunch of the actual solution. So it could tell us something because of the following. Underdamping is the fingerprint of efficient propagation. So if you have a purely exponential relaxation, it means that you have a purely imaginary frequency in your spectrum. You don't have a real part. When you have underdamping, it means that apart from some imaginary part of the frequency, you also have a real part of the frequency. So now remember that we have alignment, ferromagnetism, which basically is a Laplacian. So a Laplacian means we try to do the same thing locally. So Laplacian is a second derivative in space. So the theory we are doing is a theory we just have one derivative in time. So one derivative in time equal two derivative in space. And then this, of course, on purely dimensional level is giving you omega goes like k squared. Sorry, k is the Fourier k. And so this would give us a naive critical exponent, meaning just dimensional analysis critical exponent equal to 2, which we know is not good. Now, if you have to take into account underdamping, you need a second derivative in time to get a real part of the frequency. And the second derivative in time with a second derivative in space gives you a naive z equal to 1, a much more efficient way to transport the information. Again, these are naive values. You don't do critical exponent by dimensional analysis because you have to do RG, but dimensional analysis tells you always something very powerful or in what direction you're going. So this argument is telling us that if we reinstate underdamping, then we might get a lower value of the critical exponent. So we must go back to underdamped dynamics, which means that we must reintroduce inertia in the system. So in some way, along our road, we have done the overdamped limit without knowing it. So we're studying an overdamped system, but the system is telling us, well, the actual experiments are underdamped. So go back to the underdamped version of what you've done. So how we go back on that and why that is useful? Okay, again, a qualitative example. Domino effect, very efficient propagation, okay? Now you may say, okay, but how can I help propagation by adding more mass? This seems counterintuitive, okay? But in fact, it is exactly like that. If you do a domino underwater, which is what is done, so if you leave fixed the mass but you increase the friction, what you do is that you hinder propagation. So in the competition, which is of all physical systems between between inertia and friction, friction dampens propagation, hinders propagation, while inertia enhances propagation. Because inertia is not only the inertia to start motion. Inertia is also the inertia to stop motion, which is the most important thing for propagation in the system. Okay? So how do we go back to an underdamped system? So our third ingredient is we want to get back to an underdamped system, so we want to put inertia back in the system. Okay? So the title of this slide is Stay With Me, and then after this slide you can sleep, but it's important that you get this. Okay, so we start from this. So far, so good, okay? Poisson relation between Q and P, okay? So the important thing about this relation is that you have that P, okay, which is the momentum, is the generator of a symmetry, of a transformation, sorry, and that transformation is the translation of Q. So Q is the parameter of the transformation, and P is the generator of that transformation. And you know that when you have a symmetry, then you have a symmetry under that transformation. Then you have conservation of P, and all sort of funny things may happen when you have conservation laws. Okay? So from this you have the standard Hamilton equation. And the standard Hamilton equation, you have the reversible part, but then because you want to do stat phys, you always add to the reversible part of the dynamics an irreversible part, which is just friction plus noise. So you go to the Langevin equation by adding friction and noise to the standard Hamilton equation. And friction and noise, remember, are just the two sides of the same coin, okay? It's a way to say that you don't want to reproduce all the interaction with the rest of the system, you just sum them up with friction and noise. Okay, so you see, normal dynamics doesn't born overdamped. It starts over like an underdamped dynamics where you have all the reversible and the irreversible terms. But then you can do something which is called the overdamped limit. You can increase friction. Increase friction we compare to what? Compared to inertia. If you do that, and you may have done that at some course, what you get is that, what you get is that you go from this two equation to this equation on the right, which is an overdamped equation, which you see the force now doesn't act on P dot, but it acts directly on Q dot. Now this is where the academic world splits in two. If you're a statistical physicist, you don't even remember Newton's law. You only remember overdamped Langevin equation. You say X dot equal the force. They say, but you know, this first year they told me there was X double dot equal the force. Yeah, well, that was a long time ago. But then you have friction and noise, and then it's just X dot equal the. Okay, we want to go back to first year physics, okay? But we want to do that now in a context which is rather different because our field is not Q, is an orientational field, is the direction of motion of your fluid, okay, psi, okay? And the theory we have been done up to now is something like that, simplified. So psi dot equal to some force. So we want to get the underdamped version of that. But how do we go back? Well, by using the same kind of Poisson structure. So what do we need? We need to restore the generator of the symmetry. So you see, when you go from underdamped to overdamped, what you're effectively doing is not really to forget inertia. What you're doing is that you're killing P. You're forgetting about the dynamics of the generator of the symmetry. So what we need is to restore the generator of the symmetry. And what is the symmetry here is not the translational symmetry, it's the rotational symmetry. But it's not the rotation in the outer world, right? It's the rotation in the inner space of the order parameter. So this is what we call the spin. Because it's not, it's an angular momentum, but it's not in the rotation in the lab reference frame. It's the rotation of each single unit vector around itself. Okay? So we say that this spin will satisfy a Poisson algebra, which is the same satisfied by standard angular momentum. So S is the generator of the rotation of psi. So S is the generator of the rotation of each particle velocity around its own axis. So if you do this, then you just go Hamiltonian, and you write Hamilton equation for this dynamics, for this system, which they look like that. They seem a bit different, but it's only because you have the rotational structure. But this would be exactly the same kind of equation for, you know, the uniform rotational motion. So now psi dot is not acted upon by the force. It's acted upon by the spin. So it's the spin which is rotating the velocity, the direction of motion. And then the force given by your neighbors acts on the spin. So you're going back to standard Newton law, if you want. And then, because you want to do stat phys, you add an irreversible part, meaning which has friction and noise. So the idea is that the overdamp limit now of this new theory is the theory we have been studying up to now. So if you have a large friction, then the spin goes away, exactly like here. When you have large friction, momentum goes away. But we want to go back to this because we have experimental evidence that the system is underdamped. Okay? So once you write this kind of equation, you see that, of course, it's been already done. And if you go to see this very, very famous classic review of dynamical critical phenomena by Halperin and Hohenberg, this is a great paper, by the way, if you want to know about dynamical critical phenomena. They introduced model A, which is just time-dependent Landau-Ginzburg, which is what I showed you before, and they have all this classification of models A, B, C, etc., etc. If you are patient enough to arrive to model G, which I was not when I was a kid, but then I did a couple of years ago, model G is exactly this system which I wrote you before, but that is a model for superfluid helium in that context. But again, universality is a model in which the direction of motion, the role of the direction of motion is played by the quantum phase, but the equations are exactly the same. And this is how they look like. So these are Halperin and Hohenberg model G equation for either superfluids or quantum antiferromagnets. So you have a Hamiltonian reversible part, which is exactly the same as I told you before. So the phase is rotated by the spin, and the spin is rotated by the force. And then you can add the dissipation and noise. And if you take the overdamp limit of this equation, you get to a standard ferromagnet, model A. But the crucial point is that if you keep all the reversible terms, then here you have a symmetry, the rotational symmetry of the phase, which is telling you that the spin is conserved. So you have a continuity equation for the spin, you have a conservation law, and the conservation law is a huge game changer when it comes to dynamics and when it comes to critical exponent. And indeed, in this system, the critical exponent is not z equal 2, but is z 1.5. Notice that 1.5 is even smaller than 1.7, so that this mechanism law goes closer to the experimental value than what activity does. It's still not there, but this is telling you that the conservation of the spin, due to the fact that you have restored the symmetry and the momentum of the symmetry, is decreasing the critical exponent a lot. Because if you have a conservation laws, when you have an excitation, you cannot just push down the excitation under the carpet. You have to transport away the excitation. This is why all transport properties are changed when you have conservation laws. So what we did was to say, okay, so let's take the three ingredients: imitation, activity, and inertia. So we took the model G equation of Halperin and Hohenberg, and we did the same as Tonner and 2 did for Landau-Ginzburg. So we went active. So basically, well, it's a bit more complicated, but what we did was to change the temporal derivatives into material derivatives. So we made an active version, a fluid dynamic version of model G, which is a model for superfluids. So we get these equations. So these are the equation of our new field theory, which are complicated, and we want to study them with our G. So I will skip on the details. The important point is that it's a tough theory. Well, compared to what we normally do, of course, not compare if you do, lattice QCD. But it has 5 vertices. You have to fill, so you have propagators, correlation functions, so it's rather complicated. So even at one loop, you have a certain number of diagrams, of Feynman diagrams in the RG calculation, which we calculated thanks to some really brilliant students. And what you get at the end is that you do find a new RG fixed point. So in this plane here, you have the fixed point of pure ferromagnetism. So just imitation, no activity, no inertia, which is Z equal to 2. Then you have the fixed point when you only add activity to ferromagnetism, which is the one I showed you before, which is 1.73. Then you have the other fixed point, the one when you add inertia to the equilibrium theory. This is Halpern-Hohenberg calculation, Z 1.5. We put both activity and inertia, and so both these axes are unstable against these two perturbations. And so you have here in between, in the middle, so in a place where both activity and underdamping and inertia are relevant, a new fixed point whose critical exponent in 3 dimensions is 1.35. So this is the main result of our calculation, which took us a long time to work out. So 1.35, how good is that? Well, it is very good. So these are the values of Z of the three theories. So this is the experimental result, and this is the theoretical result. We were asked to do also some numerical simulation, which we did. We took the microscopic model whose coarse graining is our field theory, and we get a very clean critical slowing down. We've measured the critical exponent is 1.35. So this is the comparison between the 3 things: experimental, the theoretical RG at one loop, and the simulation value, which I find it remarkable. And to conclude, notice something. This is biophysics. I swear, it is. In biophysics, you're normally used to do a model with 100 parameters, well, maybe not 100, but with some parameters, let's say order 10, and to fit the parameters to the data. This is the standard business in biophysics. In this calculation, there is no parameters involved, no free parameters. We didn't fit anything, which of course it was not us, it's the greatness of the RG. So we only had to formulate 3 very general physical mechanisms, but there is no fixing, no fitting of any parameters to get that value of the critical exponent. This is how strong is universality, the whole concept of universality of the RG. Okay, these are the people involved in this calculation. I would like especially to remark the role of these 3 brilliant PhD students who did the largest part of the theoretical calculation, and thank you very much for your attention.
Thank you. Is there any question?
Okay, thank you very much. Very nice. Okay, I have indeed 2 questions that are very much related. You have shown that for overdamped it is 2 and underdamped it is 1.35 or so. This means that below a threshold on damping, the exponent changes from one value to the other.
Very good question. Okay, yeah. There is no threshold. There is an RG crossover. So the real, well, not the real, the complete situation is this one. Okay? So you have 3 crucial parameters. Not only inertia and activity, but you also have friction. Okay. So our fixed point is this one here, the one we found. So what you see is that this fixed point has an outward direction, an unstable direction. That direction is friction. And that is always true. Friction is always a relevant parameter in the hydrodynamic limit, in the Langrenz scale limit. Okay. So this means that if you have some friction, sooner or later it will become relevant and you will end up to this Z1.73 fixed point. So the question is, but your new fixed point is unstable. So the RG is telling you that in the thermodynamic limit, everything will be ruled by this fixed point. Yes, but we are not in the thermodynamic limit. So the point is that when your unstable parameter, here friction, is small, okay, you have a crossover length scale, which depends on that parameter. And for size of the system below that length scale, you are ruled by the unstable fixed point. And for size of the system larger than the length scale, you are ruled by the stable fixed point. So this is very well known, is an RG crossover. So whenever you, it's the same. It's exactly the same thing when you have standard critical phenomena. Okay. So this is T, this is TC, and you know that this is the quintessential unstable direction. Okay. So now you do an experiment, and you do the calculation here, and you get some critical exponent eta, for example. Now you do an experiment, and you find the eta coming from the RG at that point. And then they say to you, well, because you did the experiment exactly here, but you cannot do the experiment ever exactly at that temperature. So what it means that you are here, okay, but that for small enough system, meaning for L much smaller than some crossover distance depending on eta, depending on the temperature in this case, so this is not friction, it's a critical exponent, let's say nu. Depending on T, then you observe the physics of this unstable fixed point. So this is what we think is going on in this case. The very correlation functions are telling us that friction is small, because we see that we are in the underdamped limit. So it means that the size of our system, which remember they are very much finite size system, like 1,000 objects, is much smaller than some crossover length scale depending on friction. This is why we think this is relevant.
Then I have another question, which is related to some model that I know for the reasons that are particle swarm models for optimization. Have you ever heard about that?
I'm not familiar.
Essentially, you simulate the evolution of a swarm of particles to optimize a function in many variables.
Okay, yes.
And
okay.
Usually when you put the swarm, you don't put any friction. There is only inertia and alignment, essentially.
Okay.
Does it make any sense in your context not to put any friction, or
well,
give?
Okay, it's you have to be careful because the equations of motion are something like that. Let's say psi dot equal psi cross s, meaning that s rotates psi, and then s dot equal the force. So with no friction, you would have that. Okay, this is a dynamical system. It's very unstable. So you want to put friction here. However, you don't want to put a real dissipative friction. What you can put here is some coefficient lambda times s plus some noise, and you want this lambda to be proportional to k squared. That is, you want it to be proportional to a Laplacian. This is the standard way in which you have conserved friction in these dynamical field theories. And actually, this is the way of model G. In model G or model E, with all this model for superfluid, the conserved quantity at the microscopic level is the number of particles. So you cannot violate that. It has to be conserved. But you still want some dissipation. So this is why you use let's say, a kinetic coefficient which is proportional to k squared. And so this is a system which is very mild, it thermalizes very well, but still perfectly conserved, so you don't go away from that fixed point.
Thank you.
So thank you for the talk. Maybe I just didn't understand, but if I want to cast what you did in terms of the Tonner 2 equation.
Sorry, say it again?
If I want to cast what you did in terms of the Tonner 2 equations, so basically what I have to do? I have to modify the force term in their equation. So could you cast what you did in terms of just Toner 2 hydrodynamic equations?
I'm not sure I understand your question. So you're saying what we did in going from Toner 2 to our theory?
Yes.
Okay, it's not that we changed the force equation. Okay, so this is the relevant slide. Okay. So if you take the, well, let's forget about the active part. So imagine that this on the right is Toner N2. Okay, Toner N2 would be this on the right with the material derivative there.
Yes.
Okay. So how do you go from here to here? It's not that you're changing the force term. You see the force term, which is this one, it's exactly the same here. What you're saying, what you're doing is that you're reinstating the symplectic structure. I didn't want to use such a fancy expression, but what you're doing is that you're reinstating the symplectic structure between coordinate and momentum. So it's like asking what you're doing in going from, where is it? Okay, in going from this to this. Well, it's weird because it's clear how you go from the normal damped dynamics to an overdamped one. To go back from the overdamped to the damped, you have to add some information. So you have to remember that you had a momentum P, which was conjugated to Q. So the question is, how do you go back to the underdamped dynamics, to Newton's laws? So for 1600 years, well, maybe even more, people thought that the force was proportional to the velocity, right? Okay, and then Newton said, no. Force is proportional to double dot. Okay, so how did he do that? It was not such a linear thinking. It was a kind of a leap. He said, okay, no, is that Q dot is equal to P, and P dot is the force. When you add friction to this, and which is, you know, is Newton's laws or Hamilton equation. When you add friction to that equations, if you let friction take over, well, how you do the overdamp limit of this is simple because you basically disregard P dot, okay? So if you say that this is 0, then eta P dot is equal Q dot, eta P is equal Q dot, you put that on the other side, you get eta Q dot equal the force. What we just did was to say, well, maybe we didn't have to throw away the momentum. The only difference is that it's not a linear momentum, it's a rotational momentum, but it's a rotation in the inner space of the direction of motion. So we reinstated the full symplectic structure. So it's easy to go from our model to Toner N2. You simply take the overdamped limit.
Okay.
Sorry, maybe this is a very stupid question. Is there anything, any way analogous to the conformal bootstrap to compute the critical exponents in this case? I mean, is RG calculations always doable, or are there cases where you need
well, this is
smart?
Well, it's really model dependent. Well, first of all, you know, in 2 dimensions, everything changes. Yeah. Okay, so in 2 dimensions, yes, you have all sort of more powerful methods. I did my thesis with Giuseppe on conformal filtering in 2 dimensions, where you have a lot of perks. But to compare with experiment, you really need to stay in 3 dimensions. I'm not an expert of what you're asking, and it would be nice if the expert tried to do that. Also because we have been trying to do the same calculation in the low temperature phase, and it's just exploded in our face, even at 1 loop. So it would be nice to have... Yeah, well, sort of, okay, yes, but in that case, you don't have activity. So it's that plus all the nonlinearity due to activity. But it would be nice to try and explore that, but I'm not an expert of that.
Thank you. So we are a little bit over time.
There was a question there.
Should
the
we?
only
Okay.
student you can, I mean, you run into, oh, sorry, you're not a student. You look so young. I mean, that must be a compliment. Come on.
I'll take that as a compliment.
It's not a compliment.
That was a
I knew
beautiful
it.
talk. So I had 2 questions. One is, what is the predictive power of these things? So is there any predictive power? And the other one is you figured out the Z is 1.35 and what's next?
Okay, the first question is what is the predicted power?
Predictive power. Is there like a way you can predict how the swarms evolve and the dynamics
I
after
see.
doing all
Predictive,
this?
okay.
And
the
you showed these birds, bird pools which just separated and formed their own little flocks. Can you explain all that and can you predict when they diverge?
Okay,
and
yeah,
these
yeah,
kind
yeah,
of
I
things?
understand. So the predictive power is 0, known whatsoever, I would say. The next step beyond this, as I said before, would have been to try and study the low temperature phase, because this is the critical phase which is relevant for swarms, but the same exact theory applies to flocks, which are the low temperature phase, because they are all aligned, okay? So we tried to do the same calculation in the low temperature phase, and we failed, because it was just too many diagrams. We had 16 propagators, and I don't know, or the 300 diagrams, and the student wanted to kill himself. So that would have been my next step. Without that, I'm not sure. So coming back to your first question, I think that not the predictive power, but the relevance of this is to prove that RG works also in biological systems. That was not to be taken for granted at all, and indeed many people don't believe in that. So the idea that if you integrate out the small scales, you pay a price in the sense of the changing of the critical exponent with respect to their naive engineeristic values, and that's it. I think it's a huge result. It was the huge result of RG, and seeing that it at least works in one case, I think is important. But predictive power, no. It's in our group is a bad word, predictive power, so we don't do that.
Thank you. So we can keep asking questions to the speaker over a refreshment outside, and let's thank Andrea again.